Welcome everyone to this new lecture. This is going to be probably the shortest week in this course because in this week we are primarily going to talk about two topics. The first one of that is the four fundamental subspaces. So, four fundamental subspaces. This topic is more related to the previous 2 or 3 weeks, and the second topic of this week is projection. So we are going to talk about projection of a vector on a vector, projection of a vector on a vector space, and things like that. So the topics are a little different. This is more of a continuation of the last 2 or 3 weeks, and this is more like a new topic. The reason why I say this is going to be a short week is because we already know about these subspaces. So the first topic is pretty much already done. This is more like a recap or review. And the second topic is also pretty easy, as I think most of you already know the basics of projection from your school or college days. Anyway, so let's first start talking about the first topic, which is the four fundamental subspaces. So let's just get rid of this for now. Okay, so what are the four fundamental subspaces? We have the column space. You already know what it is. Column, C-O-L-U-M-N. Okay. Column space. We have the row space. You already know what that is either. Also, sorry. We have the null space. You also know what that is. Basically, as I said, all of these spaces have already been discussed in different weeks or in different or a part of different topics. So this is new, the fourth one, the left null space, but this is basically the null space of the transpose matrix, so not really new. Left null space. These four fundamental subspaces are important because Gilbert Strang, the MIT professor, who is also the writer of our textbook, he kind of mentions these four subspaces as a core concept of linear algebra, and he calls it the big picture of linear algebra. If you can view the world of linear algebra from the perspective of these subspaces. So that is why we are going over these four vector spaces again, just to put an extra highlight on them. Anyway, so let's start. Let's go one by one. What is a column space? Okay, so let's first get a matrix here, because we need a matrix for everything we do. Okay, so let's take a matrix A, which is n into m matrix. So we have n columns, sorry, n rows and m columns. So we have a matrix that is n into m. Okay. So when we are talking about the column space, let's write the columns. Okay. So we have column 1, let's call it C1. We have got C2, dot, 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 all the way to, we have got how many columns here? N into m columns, right? So we have m columns. The column space is defined as the vector space which can be spanned using these columns, right? So if we take all the columns of a matrix, and if we treat the individual columns as a vector, which is called column vector, as you have already been taught in week 6, if I'm not mistaken. So these column vectors. So we have a matrix. In that matrix, we have m different columns. Each of those columns, we are calling them column vectors. So if we span those vectors, so if we span, say, we are going to span, okay, what just happened? Okay, if we span like C1, C2, all the way to Cm, we get a vector space, right? And this vector space is called the column space of that matrix. Now, this set right here, this is not necessarily the basis of the column space, because to be the basis of a vector space, the property in itself that they span the space, this is not enough. We need one more property, which is they also have to be linearly independent. And just from this information, we don't know whether or not these columns are linearly dependent or independent, right? So although we know the first property is satisfied, these columns span the space, we cannot call this set the basis because we don't know whether or not these m columns are linearly independent or not. So let's say this matrix has r independent columns. So it's a rank r matrix. So of these m columns, we will only keep r columns which are linearly independent, and those r columns will form the what is it called, the basis, right? So those r independent columns will form the basis. How to how to calculate the basis of a column space? This topic has been discussed before. I'm going to go over that in a minute, but let's first talk about the row space. So row space is the same concept, just instead of columns we are going to take the rows. So the same matrix, the same n into a matrix, we are taking the rows now. So we have got row 1 to all the way to row n, right? So we have n rows. These vectors, row 1, row 2, row 3, all of these are m-dimensional vectors, right? So we have n vectors, r1 to rn. If we span these vectors, so this gives me the column space of A. So the row space of A is given by the span of, instead of columns, we are taking the rows, row 2 all the way to row n. And the same logic applies. This is not necessarily the basis of the row space because we don't know whether or not the rows are linearly independent or not. If we have r independent rows, which means if the matrix is r rank matrix, in the basis there will be only r independent rows. So this set spans the row space, but we still don't know whether or not this space is a basis of the row space, right? This set. Okay, so let's focus on another property, the dimension. So what is the dimension of the column space? Each vector in the column space, this is a vector of the column space, right? The first column. This vector has m components, n components, because this is an n into m matrix. So column space of A is a subspace of R n, and the row vectors, this has m components, right? So the row space of Ra is a subspace of R m. This is considering that the matrix is a real matrix, so all the values are real numbers. Okay, so column space is a subspace of Rn, row space is a subspace of Rm. Now let's look at how we can determine what is the basis of our column space or what is the basis of our row space. So we start with a matrix A, which has n columns, n rows and m columns. Now, as we said, we need to know which rows and which columns are independent, right? Because we want to keep only the independent vectors in our basis. We cannot keep dependent vectors in a basis. That is by definition. So we need to know which of these columns and which of these rows are linearly independent, and we already know how to do that. We are just going to perform elimination. So let's say we have a lot of elements here. So after elimination, you can eliminate up to the echelon form, or you can eliminate all the way up to the reduced to echelon form. It doesn't really matter. We just need to know which rows are linearly independent and which columns are linearly independent, and for which we just need to know which rows and columns contain the pivot elements, right? So after elimination, it looks something like this. So let's say we have a pivot here, a pivot here, a pivot here, and a pivot here. So we can see that this row contains a pivot element, this row contains a pivot element, third row contains a pivot element, fourth row contains a pivot element. Let's say there is a zero row after that. So the fifth row does not contain a pivot element. And similarly, the first column contains a pivot element. The second column contains a pivot element. Let's say we have a zero column here, not necessarily zero, let's say something. Anyway, point is, let's say there is no pivot in the third column. Also, there is no pivot in these columns, for an example, right? So after elimination, we know which rows and which columns contain the pivot elements. Now, when we do row operations, what are we doing? We are multiplying a row with a scalar number. We are adding two rows together. All of these are the same operations that we do when we take a linear combination of things, right? So in a vector space, we know that vector spaces are closed under linear combination. That is closed under, let's not say linear combination, let's say closed under scalar multiplication. So closed under scalar multiplication and vector addition. Vector addition. So these are the same two operations that we do when we take a linear combination of things, or in this case, a linear combination of vectors. So when we are doing row operations, we are just either multiplying the vectors, the row vectors, or adding two rows together. So the vector space is not changing, which means the row space here does not change if you do row operations on the matrix. So after elimination, our original matrix is changed. We have converted A to, let's say, RREF of A, so a different matrix. But the row space of this matrix is the row space of this matrix, because when we're doing elimination, we are doing row operations, and row operations do not change the row space of a matrix. So once we know which rows contain the pivot elements, let's say, let's take some space. Let's say we had 5 rows to begin with, and after elimination, we find that row 1, row 2, row 3, row 4, and row 5. So after elimination, let's say we find that row 2, row 3, and row 4 contains pivot elements. These two rows did not contain the pivot elements. So, while elimination, if we see that a row does not contain pivot element, they go to the bottom of the matrix, right? So after elimination, it will look something like this: row 1, row 2, row 4, and these two will be at the bottom. Should not write them horizontally, let's write them. So row 1 will be at first, not exactly row 1, the eliminated version of row 1. Then we'll have row 2, then we'll have row 4. As row 3 does not have a pivot, it will go below row 4. So row 3, and row 5. This is how our matrix will look like, right? And not row 2 exactly, because after elimination, the rows are going to change a lot. Anyway, so these are the ones that contain the pivot elements. So in our basis, we will have only these rows, or the eliminated version of the rows. You can take anyone, as elimination process does not change the row space, both will work. So I think an example would work pretty well in here. Okay, so we have our example. This is the matrix we are beginning with, A, and this is the elimination process. I did not continue up to the RREF form because I don't need to, because I already have all the information I need. So let's see what happens. We have our first pivot position here. the second row becomes completely 0, so we do a row exchange. Focus on that, this is going to be important. And after that, we do another step of elimination, so we get our first pivot, second pivot. So the row space of A can be the span. As you can see, there are only two pivots, so there are two independent rows. So the dimension of the row space is going to be 2. So the basis of the row space, one of the bases of the row space is going to be these two rows, right? 1, 2, 3, 1, 2, 3, this vector, and 0, minus 1, 0, 0, minus 1, 0. These two rows are linearly independent and they span the entire row space. So this is one of the bases. We could also continue up to the reduced to echelon form, which would probably give me something like this. Probably we are going to get 1, 0, 3, 0, 1, 0, 0, 0, 0. So these two rows, if I take 1, 0, 3 and 0, 1, 0, this is also another basis of the same row space. We could also take our basis from here. Let's see, the first and second row are the independent ones. So we take the first row and the second row, right? Not right, this is wrong, because note that the second row here is actually the third row here. We have done a row exchange. Row R2 and R3 was exchanged in this state. So although it says the second row is the independent one, in here that was the third row. So the third row is the independent one, because clearly the second row is dependent on the first row. Anyway, so we could have also taken 1, 2, 3, the first row and the third row. 1, 1, 3. Could have also taken that, and as you can see, this is also another basis of the same row space, because we just need to know which rows are independent. And we can take the basis from any of these forms, because these row exchange or row operations do not change the row space, which is not the same for column space, because when you are doing a row operation, it changes the column space. Right, let me show you. Okay, so this is the example that I want to show for column space. We have two columns, and this is the original matrix, and this is the matrix after a row operation. So I have added row 1 with row 2, so R1 is equal to R1 plus R2. So this row operation gives me this matrix. So the column space of this matrix is the span of these two vectors, right? This vector and this vector. Let me show you the graph or the visualization of it. All right, so we have our two vectors, the first column 151 and the second column 331 here. So I have plotted that in a three-dimensional space, and as you can see, the blue plane here, this is the span of these two vectors. All right, so let's stop and let's do the row operation, which is just adding the first two rows. So we have 151 first two. If we add the first two row, we are going to get 651 as we saw. So this is 651. Instead of 331, we are going to get 3 plus 3, 631. That is not 6. Okay, so as you can see, this is a completely different plane. And please remember that this plane is what represents the column space of the matrix. So as you can very clearly see, after doing the row operation, our column space is completely shifted. So what we can learn from here is that row operations do not preserve the column space. They preserve the row space, but they do not preserve the column space. Which means, let's look at this example one more time. This time, the same matrix, the same elimination process, but this time we are trying to figure out the column space. So there are two ways to do it. One, you have already been shown. Transpose this matrix, all right, because the column space is the row space of the transpose of A, because when you do the transpose, the columns become the rows and the rows become the columns. So that would be one way. You transpose the matrix and then determine the row space of that transpose matrix, which will give you the column space of the original matrix. But if you don't want to do the elimination for two different matrices, one for A and one for A transpose, you can skip that. You can just do the elimination process of the original matrix A, which you did to determine the row space, and from that you can also determine the column space. Alright, so we just need to know which columns are independent, right? And we have pivot in our first column and our second column, right? The third column does not have any pivot, which gives me that the first column here and the second column here, they are the independent columns, right? So we are going to get the basis of the column space, which is 1, 2, 1. This is one of the bases, but we just need any one basis, right? 2, 4, 1. This is one of the basis of the column space. Just remember that you cannot take this column and this column, or this column and this column, because this denotes to a different column space. You have to take the independent columns from the original matrix, because as I showed, after each row operation, the column space becomes something else, a different space. So you just get the information of which columns are independent and use that information to get your basis from the original matrix. All right, so that is how you get the column space and the row space. Pretty easy, right? In the next part, we're going to talk about the null space and the left null space.